So we are Code Intelligence, a company from Bonn that two colleagues of mine and myself founded with our professor after we were done with our PhDs in order to try to provide a usable way to apply fuzzing in order to secure software. So I guess this photo might look familiar to many of you. So this was 2015. A car on the highway was hacked by two hackers. So this car was connected to the internet. They managed to hack the car and take full control of the system. So they could kill the engine, they could kill the brakes. So basically they had full control over the car. A second example, a more like a more prominent one is this a casino was hacked by hacking. So there was a fish tank, and inside this fish tank there was a thermostat. That was an IoT device, and it was connected to the casino Wi-Fi. So by hacking into the thermostat, hackers managed to, through the Wi-Fi, to get into the internal network and steal customer private informations like credit card numbers, for example. So this, even like this case that you wouldn't even maybe think about it, caused losses in millions of dollars. And maybe another example, a personal one that I found like a few weeks ago by one of the largest company in the embedded sector in Germany. Basically, they had a serious security vulnerability that enabled an attacker to write unlimited amount of bytes into the buffer. So it was a buffer overflow with no sanity checks. So this and bugs are really difficult and are really expensive. And there's this rule of 10 that a bug becomes more expensive, more difficult, the later you discover it. So we have in the design phase, then comes the unit test phase, and we have the system testing, acceptance testing. So at each phase we are late to discover the bug. It becomes 10 more expensive, 10 more painful. And so currently, what usually we do manual penetration testing and manual testing at the acceptance test level, and we seem to. I think we need to do a better job in doing automated software testing on the unit test level, so that we can discover like most of the bugs that can be discovered at this level, and then like allocate the pen testing resources for like finding the bugs where actual human intelligence is needed. So if we think about this, so what's the main reason that bugs in software and security vulnerabilities are becoming increasingly, so we're discovering more and more bugs every year? And actually it's because of this guy here. So the human, so us, the developers. So humans, so we'll make errors. Humans, we have strict deadlines that we need to catch. So even the best developers, they make mistakes, and when they have like deadlines, and when the time pressure increases, so they tend to improvise, to design some shortcuts. So we end up with some creative solutions that are maybe not the best ones, but that would work in this case. So, and this more or less represents some of the code patterns that we actually see at some like production code. And I think we need to make a better job here. We need to make this better. I mean, we need to like make the software quality much better. And if we look at the situation. So definitely we cannot change the human nature. We'll also always do mistakes. We'll always underperform under pressure. So we need some automated tools, automated approaches to help us improve the quality of our code. And so quite a popular approach is static analysis to detect vulnerabilities, but static analysis has several fundamental issues that you cannot construct a complete and precise representation of the program. So for example, in C and C++, you have function pointers and you have polymorphism. So it's not possible to statically represent the whole program state. So tools make over approximations. They simply look for some patterns, and static analysis as a result has lots of false positives that it becomes sometimes unusable. So with one case that we tested some software, and there was a report like 7,000 pages, and you wouldn't have enough resources to even have a look at the code. And more importantly, with static analysis, you don't have any information. If a bug is reported, is it really a bug? How can I trigger this bug? So for this, we need dynamic approaches, and fuzzing in the recent years has been the most effective approach to find bugs in software. So who of you have heard of fuzzing or have? Okay, cool. So I'll just give a brief introduction. So what fuzzing is. So usually, we write unit tests, right? So we have here our system under test. So it's the system that we want to test, and we have some data here, this image maybe, and then we give this data, we call to our unit test, and we check if our software behaves as it should. So okay, this good step. So when the next step was, okay, how if we just mutate this image? So if we just change our data a little bit? So and this gave rise to black box fuzzing. That's we simply just did some random data, and check if the program still behaves correctly. So we can flip the image, we can change the colors, and we can so do some mutations and check if it behaves correctly. But then the thing is, so if you do this, you don't have any information. Is the inputs that I'm generating, are they good or not? Are they revealing more code paths or not? So so in the recent advances in the domain of fuzzing is coverage guided fuzzing. So what you would do is you would instrument your program under test in a way that it gives you coverage feedback. So you have one input, you execute this input, and has a feedback, has a sort of a report so the code places where that my input went to. So with each input, the fuzzer would know, okay, I was there, I saw now new code coverage or not. And then he can, or it can, by observing the program states and the feedback, it can just optimize the mutations it does in order to reach more code. And this is automated. So current state of the art fuzzer would try several mutations, would flip bits, would change byte, use some magic numbers, and they will just feed it to the program under test in the hope that the program would crash at some point. And it's this feedback loop that would give the fuzzer information where the code was. So which code blocks have I already seen or not. So from a program point of view, so this illustrates the difference between testing and fuzzing. So for testing, you write concrete test cases that calls your API that you want to test with concrete inputs, like input 1, 2, and 3, 4. With fuzzing, you have this endless loop, and with each iteration, you get some input from the fuzzer. You ask the fuzzer to provide you with an input, and the fuzzer would provide this input in a way that it maximizes code coverage. So at a high level, the fuzzing algorithms work this way. Basically, you start from an initial corpus, which are basically a set of seeds, a set of inputs for your program, and the fuzzer would just take one input from this queue, would mutate it, and then it feeds to the API, and it checks, did I find new code coverage with this input? Yes. Then if yes, then it will be put back into the corpus. If no, it will be just discarded. So this sort of like mimics the evolution. So each generation of inputs, they survive if they lead to new code coverage. So with time, you get code, you get inputs that reach deep in the program. And with one use case, fuzzer AFL, so they tested a JPEG parser, so an image parser, and they start with a seed corpus containing one text file. And after 8 hours, the fuzzer has managed to generate valid images, valid JPEG images, because it just mutated this bit and byte and checked this doesn't lead to new code coverage. I just discard it, and after some time, it manages to provide valid inputs. So basically, this is the general algorithm for fuzzing, and yeah. So basically, as we see here, we need two components to effectively do that. We need to measure code coverage, and we need to know that something bad has happened in our program. So these are the two most important components in fuzzing. And so as I just said, for code coverage, so the program is instrumented. So when you compile your code, you add these markers in the code that will give the fuzzer feedback when it reaches a certain code block. So the fuzzer would know, okay, I was here, I've seen this loop like 20 times, so it has exact information about the code that was covered by each input. And you need a way to detect errors, because not all errors can cause the program to crash. If you have a read buffer overflow, this wouldn't crash the program, but basically you would leak some information. So these sensitive errors, we use the Google sanitizer, are pretty famous. Does anyone have worked with the sanitizer before? Okay, so just give an overview about what these sanitizers are. So sanitizers are like basically runtime checks that are inserted into the code. They make your program crash faster, and they make your program much slower. So they're pretty good. Yeah. You don't want this in production, but you do want this while testing, because this would enable you to find bugs, even subtle bugs, much quicker. And so basically it's basically this is the goal of the sanitizer, to detect read overflow and crash when a read overflow happens. Of course, you don't want to do this in production. With the production, you don't want sanitizers, but testing, because you have much stricter requirements about the program state. So any read overflow, even if it's by 1 byte, this will cause a crash. And you can detect several stuff like data leaks, data erasures, memory corruptions, and undefined behavior. So there are several types of sanitizers. You have the ASIN or address sanitizers. Basically, it's used to detect some memory corruption errors like buffer overflows, use after free, and such errors. And it works by having a shadow memory, and with each allocation, it also intercepts malloc. So with each allocation, you add some red zones around the area that you allocated, and if you reach any of these red zones by a read or write access, the address sanitizer would crash. There's also like a thread sanitizer that you use to detect data races, deadlocks, and also the undefined behavior sanitizer. But as you see, so each sanitizer has a CPU and memory overhead. So with the address sanitizer, the program becomes almost 2 times slower, but you detect the bugs faster, and you only want to do this while testing. And if you compare, I'm not sure if you used Valgrind before. It's also a memory tool to detect these type of errors, and address sanitizer is by an order of magnitude faster than Valgrind. So, and here I just give an example of a fuzzer, of an open source fuzzer that's part of the CLang and the LLVM framework. It's called libfuzzer, and with libfuzzer you can basically test your code, test your APIs, and libfuzzer is really quite intelligent and in generating good inputs. And basically how you would use it is, let's suppose here you have an API that you want to test. It's called feed data to my API, and you would just need to write function that's called LLVM fuzzer test1 input, and it has this signature, and you basically call your code from here. And what would happen here is that this function would be called from the fuzzer, and data and size represent the data and of the random input or the mutated input, and size is the size of the generated input. And basically you can here provide some code or do some initialization, and then call your API with this random data. And in order to detect these errors, you need to, for example, in order to run a fuzzer, you would just need to compile it. Here's an example of CLang with the option -f sanitize fuzzer. This will insert into the code coverage instrumentation, and you can also add further sanitizers. You say, okay, I want the address sanitizer, or I want the thread sanitizer, etc. So you need to provide these compilation flags, and this would compile your code with code coverage and with sanitizers. And this is the output that you would get when you run a libfuzzer fuzz target. So you get an executable that you can directly run. So basically what libfuzzer would do is just have a main function around this call, and around this function that will call this function in an endless loop. And here you see information about the code coverage that's reported by libfuzzer. So you want to make sure that the coverage go up while you're testing. So this way you make sure that the fuzzer is finding new inputs. And here is where the sanitizers are really useful. So you get a crash, and here you say the information. Okay, this is a crash caused by address sanitizer, and it's a global buffer overflow, and it has a write overflow of this size, and you get here the complete stack trace that you can analyze. So this is the driver, and this is called this function, and this is the replacement of memcopy that ASIN provided. And you get here you have the file with a concrete input that caused the program to crash, and you have also a text representation of it. So any questions so far? Cool. So we saw, okay, and fuzzing, just to give an some words about the effectiveness of fuzzing. So last year, fuzzing found 14,000 bugs in Google Chrome. So, and Google Chrome is like one of the best products. So it's really, they have really well engineers. They have a large team of security experts, and even though they missed 14,000 bugs that were found by fuzzing. So fuzzing is currently the main testing methodology by Google, and they have teams of PhDs experts that they just have. But for some reason, even with this, like, fuzzing is effective, but nevertheless, such things happen. So Heartbleed, it happened, it was discovered like a few years ago, but basically Heartbleed, it was introduced in 2011, and it took over 2 years to be found. But you can show that with current fuzzers, with AFL, it's another fuzzer, you can manage to find it in 6 hours, and even with libfuzzer you only need 10 seconds. But nevertheless, it took more than 2 years to be found. And I believe that the reason is that fuzzing was not performed by the developers, so it was not used by them. And developers maybe have other things to worry about. They have their deadlines. So, but I think is that they need some more usable tools to be able to apply fuzz testing as part of their job. So with this, I come to some challenges that we discovered we encountered when applying fuzzing to real-world software. So there are several challenges where the current state-of-the-art open source fuzzer have severe limitations. So one of the problems is that many codes, it doesn't run on x86 or x64. Especially in the embedded world, you have your own operating systems, you have code that interacts with the hardware, you have other architectures that ARM and MIPS. And actually, one of the most effective way that we found to apply fuzzing to these cases was to basically cross-compile it for x86. So you don't have to cross-compile the whole application if you have a certain module that you can sort of isolate and make it runnable in x86 or x64 architectures. You have the benefit that you can use the current tools without any changes. You can also have it run your test in a more scalable way by running like several instances of the fuzzer in a CI/CD deployment. And for this, of course, you need to mock the hardware test, maybe fake some devices. And we made quite a good experience with this when we tested embedded software. And even we had the case where we tested some sensor and it has some inline assembly, but basically the module that would parse the inputs from the outside did not use the inline assembly. So by just commenting out this code, we were able to compile it for x86 and found several issues there. In cases where this is not possible to run or to cross-compile, which we've never had to do before, basically you can cross-compile the LLVM toolchain with a libfuzzer into your architecture, and basically build fuzz targets for the architecture on which you want to test your software. And there you can use QEMU. I think QEMU is known. It's an emulation framework, and you can either use it in the user mode. So if you have an isolated module, you can just compile it for your architecture, and it will run on the BC because the user mode works with binary translation, or you can go a little bit further and run a full system emulation where you can emulate your devices and run fuzzing there. So the second challenge that we found is there's some roadblocks when applying fuzzing, because as we just saw, in order to correctly do fuzzing, you need to use sanitizers. You need to compile your code for code coverage. So you would need to do some changes to the build system, and you would need to change the compiler flags, to change the compiler themselves. And this is, well, if it's like CMake, it's easy to use, but we saw also many cases where like the build script or the build system was a bunch of build scripts, and they were not configurable. So it's really hard to do this manually. So the solution here, our solution was, okay, regardless of what you use as a build system, at some point at runtime, the compiler will be invoked. So if you just have a build system interceptor that runs below the build system, and so you just let it run, and at some point it will call the compiler, and at this point we can do this at runtime, just replace the compiler, remove some compiler flags, add some compiler flags that you want, and this would basically compile the code in the way we want it without the user ever having to touch his build system. And this is quite useful because, as we saw, we have different sanitizers. Some of them, they cannot be compiled together, so they are mutually exclusive. So you cannot run address and memory sanitizer at the same time. So, and you don't want to just change your build system for each fuzzer and for each sanitizer. So this is, with this way, you can just make it configurable, and the changes will be done anyway at runtime. So this would save quite effort on the developer side. So one of the most important challenges or the most important use cases that we found is we call it structure-aware fuzzing. And the problem is, well, fuzzers, they have some, or libfuzzer, for example, it has some mutations. So it mutates some bytes, it mutates some bits, it deletes some parts of your code. But what if your program actually expects a structured data, a data that has to be according to a different, special structure? These mutations will lead your data to become invalid, so you will not be able to reach deep in the code. And this problem is illustrated here. So suppose we have a JSON parser. Our API expects JSON, and if we have a JSON parser, and then if it's a valid JSON, then the input is the message is being forwarded to the business logic, and that communicates with the database at somehow. So, and we say, okay, good, we want to apply fuzzing for this. So, as we do usually with fuzzing, we provide some initial data. So this is a valid example for the fuzzer, so that he can use it as an initial seed corpus and start mutating it. But the problem is, and so this input would reach the business logic, but when the fuzzer now starts to do some mutations, this will totally break the structure that you're expecting, and then the fuzzer will end up just generating data that are invalid, and that will end up being rejected by or too early in the program, and you would not be able to reach your business logic. So the fuzzer would try again and again until at some point it might generate something valid. So, and this is quite important because not like in many cases you don't have APIs that basically only consumes row buffer. You have APIs that expect certain data types, that expect certain structure. And for this, you need the structure-aware fuzzing, and this is libfuzzer. So libfuzzer has an API to build on top of it. So it has an API, two functions. So it's LLVM fuzzer custom mutator. It's a API function by libfuzzer, and here you can you get the data and size and the seed, and basically you can provide your own mutation. So if you have a special requirements for your input, you can provide your own mutations. And here, if you're inside your custom mutations, you want to still mutate some strings. Like you have a struct that has a string, and if you want to mutate this string using the original libfuzzer algorithm, you can just call LLVM fuzzer mutate. So actually, libfuzzer provides a way to do this, to have custom mutator. So what we can do here? So what you can do is you have to come up with some. That's what we did. Also, you come up with some language, some way to describe your structure. And as an example, we use protobuf, protocol buffers. Yeah. So protocol buffers is a way to represent data. It's from Google, and basically you can describe your structure, and it's type safe. It's quite compact, so it has a binary representation, and there's a compiler that generates parser for your grammar, and for different languages, for C, for Java, Go, JavaScript, Python. So it's quite a good way to present data. And you can say, okay, I need a way. So if I have a protobuf message, for example, I need a way to mutate it. So that in a way that I would also always generate. So if I mutate a message, I need the result should be a message that expects my definition. And one tool that we use here, it's called libprotobuf mutator. Yeah, surprise, surprise, also from Google. They have a way they have implemented a mutation library that mutates protobuf messages. And basically that's all what you need. In addition, that you need a way, so if you have a protobuf message or a message that's according to your definition, a way to just convert it back to your struct or your data that need to be fed to the API. And with this, you can do a lot of things. So you can define a way to define the structure of your application. You can do some fuzzing protocols, so you can define the messages that a given protocol expects, and then you make sure that your fuzzer generates valid messages. And so to show an example of the effectiveness of this approach, here are two examples of two use cases that we fuzzed. GBGMe, so it's GBG made easy. So the idea is to have a easier crypto API, so that you can access it also. So you can use GBG from the browser. And they have a client that receives JSON data from the browser, and the commands need to have a specific set of commands in this JSON request. And basically, if you would fuzz it with a vanilla fuzzer without any modification, you see here after five hours, fuzzer was not able to produce anything useful. If you add a structure-aware fuzzer for this, where we have a JSON and we know the commands, and we use the grammar mutator, you see that fuzzer generates way too more code coverage. So this is the code coverage information that are reported by libfuzzer, and here you can think about code blocks that was reached by the fuzzer. The same thing was we observed while fuzzing MongoDB. Fuzzer would reach some code, but with the grammar, so it knows the structure of the of the nbot, and that's why it can generate much more code coverage. So what you can do with this idea is that let's assume you have your API, you have a struct that has 3 values, 3 items, 1 buffer and one integer, and then you have an API function that consumes a struct type. So this would not be easy to do with open source tools, because they only what they give you is data buffer. So with this approach, you can do stuff like this. You can say, okay, I want to have to fuzz this struct, and what you would do here, what we will do here is, since we know the type, so with static analysis, you know the AST, so you know this type description, and from this AST you can automatically generate a protobuf message that represents this type, and based on that, you already have with libprotobuf mutator already mutations that would respect the structure. So this way, the fuzzer would all the time fuzz or generate valid structs. So you wouldn't have to do this conversion yourself. And then you can do stuff like, okay, for the fuzzer, I want, or this my string size is the size of my string. So the fuzzer knows, okay, I don't have to mutate the last field because it's the length of the second one. And this is quite useful. And so because you don't have to reinvent the wheel each time, you can basically say, okay, I want to fuzz this struct, and everything will be taken care of automatically. Yep. Yeah, some more challenges, like as we saw, we just need to write some code to be able to fuzz. So writing fuzz targets, and this is similar to writing unit tests. It can be quite a time-consuming task. So we need ways to automatically, or to at least, or semi-automatically helps the users or developers to write fuzz tests. Stateful fuzzing is something that you can do with, if you have this framework or this framework to define data like grammars. You can define a grammar as a sequence of messages. Like this is what you have when you want to do some, if your software expects a state, so you want, it's not that you only send one message, as we saw in the open source tools. You need a sequence of messages. Maybe you need some login or hello, or this interaction between with the software. You can also define it as a grammar, and the fuzzer would generate valid sequences for you. And it will try to also mutate the order of the sequence to see if there are some transitions in the state you just didn't see. Another interesting area of work or of research is better signals to guide the mutation engine. So now we use code coverage, but there are some ideas where we can do something called directed fuzzing. Is that with static analysis, or you can identify the location in the code or the blocks in the code that are more likely to cause problems. So you see, for example, here like a lot of memcopy stuff, like pointer arithmetics, and you can try to guide the fuzzer to reach this basic block. So it's called directed fuzzing, and it's also a promising area that we're working on. Yeah, of course, we have the sanitizers, but for some other scenarios, you may need more bug detectors. And yeah, so what we currently saw is C and C++. What about other languages? So for Java, and I think Java is also becoming relevant even in the embedded world, because there are like Java 4 embedded systems. There are some companies that are using it. But I mean, apart from that, Java is one of the most used programming languages, and their fuzzing is really needed. So, as a summary or the takeaways from my talk, we saw that human factor, or that I believe human factor is still and will be the main reason that we will always encounter security vulnerabilities. And so we also saw that fuzzing from the experience is currently the most effective way to trigger these bugs. We saw that also open source tools, they are great, but they have several limitations when you get to test real world software. And we need solutions for developers. We need to be able to assist developers to do security testing themselves with the minimal overhead, because their focus will be always on like more features, writing software. So this, and as I said, the earlier that we find the bugs, the better it would be, and the easier is to fix, the least expensive it would be. And we believe in fuzz-driven development. So the best way is to write fuzz tests for your APIs, and this would be checked in with the code, and ideally you would run fuzzing maybe after each commit, or at merge requests, or at nightly builds. So you need this continuous way to test your software. And like the thing is, so with fuzzing, it always builds the seed corpus. So it will learn over time the structure of your software. And if you find a bug, okay, you fix it and you add this bug to the seed corpus so that you make sure that this bug doesn't happen again. So fuzzing is quite effective. We need to make it more usable. So that's our message. That's our vision. And with that, I come to the end of my talk. And I would like to show a short demo of what we did. Okay. Here. I hope it's... So this is VS Code, and this is here one of the things that we developed is plugin for VS Code, and this plugin simply interacts with the backend using gRPC, and so I just need to get my cursor. So this is the code that we're testing here is, or that we see here is Zint. So it's a library that's used to generate barcodes, and it's used by some. It's a C library, and it's used by embedded printers that print barcode, and it's one package in Fedora. So this is the plugin. You see that. So what we need, what the tool needs is just to know how do you build your project. That's all. So, and this is what you see here, and you create fuzz testing for the project. And of course, for some build systems, here it's CMake. The tool can easily generate suggestions. So with this script, you can build your software. Of course, you can change it, you can adjust it. And the next step here is called initialize project. So here, what we do is we build the project once. And here we build the project with our interceptor. So here you're seeing you see the build system output, but in the background each compiler invocation is intercepted, and then so that we build from that what we call it's known as compilation database. So in the compilation database we keep all the dependencies. So we know this object file is a result of compiling this source file with these options. So you have, you can track all the dependencies, and they include so the link time dependencies and the compile time dependencies. And this would enable us to do stuff like this semi-auto generation of fuzz target. So what you would do here is, for example, you see here's the backend, and the code has some tests, which is quite good. And what you usually do is you can have a look at the tests, and here you see, okay, test library seems interesting. And so this is the way where they test the library, and you see, okay, there's a function called something encode. So any function that has encode or bars or in the name, it's a good candidate for fuzzing. So you can just go there, and so you see this fuzz this function. So we do this, or we can do this, because we build the compilation database, so we know exactly where the functions are, and for each functions we know the dependencies. So for this function is in the source file. In order to compile this source file, you need this link and compile time dependency. So you can see, okay, this looks good, I want to fuzz this function. So what would happen is that this would create for you this fuzzer template with all the includes automatically generated, and also if you want to have more insight, so this is what have been generated, and also the link time parameters, so you know them before, because we have this compilation database. And then, okay, good. So you can say here you can basically write the code that would call the API. So for this, I have already created the code here. So here is the actual code. But basically, it's the same includes with some cleanup, and basically I just write. So we just wrote the code that would actually code the library in a meaningful way. So but everything like the includes, the link time dependencies are automatically resolved. So that's what we say about trying to help developers as much as possible when writing fuzz targets. And then you have to define a runtime configuration. So you say how long this fuzzing run should take, and which fuzzer should be included. And if we go here we see this is the test collection that we defined. And you can say, okay, I just make it a bit there. Okay, this is my test collection, this is my runtime definitions, I want to run it. So what would happen now is we'll do some initializations, and here it's building the project with all the needed instrumentation. So we're building the project for the address sanitizer, and as you just saw, I didn't have to tell the tool like use this flags, use fsanitize address, use change the compiler invocation. So this is simply a setting that okay. So this is simply a setting that already configured, and we do it with like, because we intercept the compiler invocation at runtime. And see here we see that it was quite fast, and it found the error. So it found one error, and this was really fast. It took only a few seconds. And here you see information about the code coverage. So you see when the fuzzer finds a new input that leads to a new coverage, this will be reported, and you see how many unique input had the fuzzer generated. And okay, now we have found a crash, but we need a way to fix it. So we need to fix the crash. And if we go here, and we can see, okay, now this crash was found and is a stack buffer overflow. You can get also more information about the stack, about the error, the complete stack trace, and what happened. So this, we have a write of this size, but if you want, and you get the concrete input, so basically you get all what happened to cause this crash. And this is actually the good thing about fuzzing, is that with each crash you sort of have a proof. This is the input. If you try this input, your program would crash. And as a feature, like, okay, to help users to understand the crash more or better, we have this debugging feature. So you can just click here, okay, this is the crash, I want to debug this crash. So what would happen is the debugger will start it automatically, and we have here from the stack trace what you got from the fuzzer, we can set the breakpoints. We set the breakpoints automatically, and so basically you can step through the code, and at each point here you have like the concrete inputs, you have the concrete state of your program, so that it becomes much easier to analyze. And because this was actually a bug, and this is like a real world software that's heavily used, and the fuzzer has managed to find the bug quite easily. And so you would basically analyze the crash in the debugger and then try to know what went wrong. And this is actually the problem was that, I mean, it was not enough space allocated for this variable. So this can be, if I just fix this now, okay, I found the crash. Let's assume I analyzed the code with the debugger, and this crash was found. Okay, I said I want to verify is it the real fix or not. So you can just go back here and run the code again. It'll compile the code with your adjustments, and it will compile it with the same configuration, with the same sanitizer, with the same flags, and now okay, so now it will start a second run. Oh, it found a second crash, I guess. Yeah, it seems that there are like further issues with the code, but I mean, this is the idea, is that you have you need a usable way to configure your fuzz target, and you need a usable way to understand the errors. So you don't want like the most you automate for the developers, the easier their task would be, and the easier they would have an easier time understanding the problems and fixing them. And so the idea would be, okay, here now I set a fuzzing, I have a fuzz target, then fuzzing should be set up in the continuous integration, then that your code is run with each commit. So basically, one thing that that we have is you say, okay, now I want to run this in the continuous integration, and then you can choose which continuous integration you want to run. You check the test collections or the run configuration that you want. You check how you want to be notified, and in the current states you would get here automatically a like for GitLab runner YAML file that you can put in your GitLab CI that fuzzing would run in each with each commit, for example. And so here, just one last thing here. The last step is for each fuzzer we create a Docker container so that you can simply just push your fuzzing or your fuzzer to a cloud where you can just run multiple instances of it. So here, as I just said, so our goal is trying to make fuzzing usable and effective, usable for the developers and effective to be applied on real world software. Thank you. Yep. So that's what we actually did. So I said that like the best experience we did with just cross compiling it for to be run. So either we just cross compile it to be run on a x86 system, and then you can emulate the CAN protocol or the CAN interface using structure aware fuzzing. So we have a framework where you can easily say, okay, my interface is structured in this way. The messages looks like this, and here you need the sequence of messages. And for that, the fuzzer will be able to generate valid messages for you. The thing is, so if you want to have a scalable testing, you would try to prevent having hardware in the loop, so that you have a way to, well, the other way, like the use case of fuzzing or testing on the real hardware, this is still possible. So you can fuzz a component and by forwarding the inputs to your hardware. But from our experience, we did the best experience when just we cross-compile the component that you want to fuzz for x86 and fuzz it there. Yep.
Yeah. Especially in that example, I would imagine that a lot of potential errors are also things like race conditions or even hardware bugs, for that matter, that are not going to show up in the cross-compiled version or even the instrumentation version. On the other hand, if it's a car, it's probably not an ARM Cortex. But if the processor has a trace macro cell, then you can usually do there's hardware facilities in the chip to do a trace of code coverage, and you can also inject values through the debugger and I think it would be conceivably possible to do
I'm not saying it's not possible, but
it's probably man years of work. But
yeah, of course, it's a lot of work. That's why it's for many use cases where you have errors like buffer overflows. If you cross-compile it for x86, you will still find the buffer overflows. And exactly. So there are some types of bugs that you can find by cross-compiling your code into x86 or x64. There are other types of bugs maybe that you want a more like realistic environment for the code to run it.
Stack Overflow is probably, when cross-compiling, you're not going to find out of memory. You're not going to find, violations of latency guarantees because of fragmented heap.
Out of memory, you can tell the fuzzer, like for libfuzzer, for example, you can say it crash if the memory allocated was more than X megabytes, for example, or X kilobytes. Then you will get an out of memory error.
Or X kilobytes. Yeah, okay.
Yeah. Or you can say there are some also called slow units. Like you specify if the executions take more than of my fuzz target for each iteration takes more than X milliseconds, or it depends on how you define it, just produce a crash, and it's called slow unit. So this is all these parameters are configurable for the fuzzer.
We don't do any fuzzing right now. Can you give me sort of a ballpark gut feeling of like how many days of training do I have to buy for my team to start doing this, or like how involved would it be for us to set something like this up for our design pipeline? Actually, or our development pipeline?
So we also did this with some large companies with large projects, and usually like you first need some maybe initial training with the tool, so how the tool works, but like after you will have some initial overhead to set it up, few days, and then after that, like creating fuzz tests becomes really easy. Yeah. And this is exactly so. This is a real example that we saw at one of our customers. So, but the thing is here, the code can be on without problems be compiled to x86 with some other use cases where we had really embedded software that's intended to be compiled for other architecture. You just need to invest some efforts, few days to cross compile it. You will not maybe find everything, but many bugs on the application level you would easily find. And you have, and this is something that I show with the struct fuzzer. You can, and this is not possible with the current solutions, like with the open source solutions. You can just, I want to fuzz my struct, and usually you have like several structs in your application, and then you would make sure that the fuzzer would generate valid structs, and the initial overhead is like few days to set things up, but after that, this is a realistic example of how easy it can get when you set this up to generate new fuzz targets.
I was wondering, when you have fuzzing in your continuous integration pipeline, how do you store your corpus of inputs? How is it reused in the next run? And how do you configure the fuzz time? So can you let the machines go fuzzing until the next commit comes?
You can do that, but I think when you set up fuzzing for the first time, you might need to, or you would need to run it a bit longer, like so that the fuzzer would explore the program state and generate like a good seed corpus. But after that, like usually each commit you have some minimal changes, and you don't want to run it for like 3 days. You can just run it for 10 minutes because the fuzzer already sort of learned from the previous runs what are the endpoints that would maximize the like the code coverage for your code. Regarding the first question, how do we store the seed corpus? So we have so we do our tests in a CI mode in a Kubernetes cluster. So basically, in the CI, you would like build your projects and build the fuzzers, and what comes out of this build process is a Docker container. that contains all the dependencies of your project, and this gets pushed to our, or it can be our, or it can be your Kubernetes cluster, depends how you configure it. And you can say here, for this test, I want to run 10 instances, for example. And so these will be run in the Kubernetes cluster, and there you can use it, store the seed corpus in an NFS or something like that. So this is how the CI/CD setup would look like. Okay, thank you.